Greetings, everybody. Welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla. Today we're taking a look at reflection and refraction. So, let's imagine we have a ray of sunlight that's coming through your window. The sunlight is hitting at an angle of 30 degrees to the normal. We'll talk about what we mean by that in just a moment. The index of refraction for air is approximately equal to 1. We'll just round off to 1 for simplicity's sake. And 1.50 for the glass itself of the window pane. And I have the following questions. What is the angle of reflection off of the glass to the normal? What's the angle of the light passing in the glass itself? Is that the same? And if it isn't, what is it? And if the angles all change, what does that do to the angle of the light once it passes through the window pane and is inside your house? So, those are our questions. And the picture here is meant to represent a little bit of that idea. By a normal, we mean a normal line or a perpendicular, imaginary perpendicular line that is perpendicular specifically to the surface. So this is, say, the outside surface of the window pane right here. And we can sketch in a little dashed line to represent that idea. Angles, in this case, are always measured from that. So notice they're not measured from the surface. They're measured from this perpendicular or normal line to it. That is the same usage of the word normal you've seen in Physics 1 for the normal force, for example, right? That was a force that's perpendicular to a surface. We have a very similar usage of the word in this case. Now, the angle inside the glass would be this angle here, for example. What's that? But also, that will be the same as this tiny angle here. So these skinny angles here and here will turn out to be the angles of interest inside the glass. When the light ray comes out of the glass and enters the air into your house, that'll be this angle here. Okay, so notice again, it's always measured compared to a normal. Now, because there's a shift in position of the light ray, goes from, say, here to here, going sideways, the normal has to adjust too. So when we're talking about a normal, we're talking about the normal of, say, an interface, if you will, between two substances. In this case, outside air and glass. That normal line is sketched here. If we're talking about, say, from the light ray going from the pane of glass to the air inside your house, that interface or boundary is here. So notice that there's two different, say, normal lines sketched for that reason. All right, so let's go ahead and get solving on our questions. The first question is about the easiest thing you'll ever do in physics. By definition, or not by definition, but very simple to find out, angle of reflection, I'll write it like that, is equal to angle of incidence. They're the same thing, which means in our example here, 30 degrees. No calculation necessary. So if I were to sketch that, that ray would then be going back outwards like this, and this reflected ray comes off at the same angle. Now notice it's going that way. It's not going straight back where it came from, right? Reflected means it's going to bounce off in the other direction, but with the same angle. Okay, so that's the first one. No problem there. Now, what about the next two questions, the angle inside the glass, or more specifically, changing the angle from air to glass, and then from glass back to air? Where's that formula come from? Before I solve those questions, let me write this way. This is called the law of refraction, and a law is typically written in a fashion that looks something like this. So little n stands for index of refraction. It's basically, and we'll see this towards the end of this episode, this is basically a measure of the change of the speed of the ray. Very short, light rays slow down when they pass through something. The speed of light that's all famous, the 300 million meters per second that you're familiar with seeing, that is specifically the speed of light in vacuum. It's always famous for being the fastest speed ever possible, so on and so forth. That's strictly true in a vacuum, though. If you have light passing through a substance, then it will be traveling at a different speed. It'll be a slower speed. Now, air is very close to vacuum in these respects, and so that's why we've rounded off. So the index of refraction, the speed of light doesn't really change appreciably in air. It's less than 1% change, so we're going to ignore that for our purposes here. But you can't ignore that for glass or other clear substances like water or plastic, clear plastic, or diamond even. Then that number matters, and it does affect what ends up being seen. So the law of refraction This is the law of reflection. Law of refraction talks about this. So index of refraction for one substance, index for the other. What are these signs? This is sine of the angle coming in, or the sine in substance 1. So notice index of refraction 1, sine of angle 1, is equal to index of refraction 2, sine of angle 2. And again, the angles are measured compared to those normals. So, as we always do in physics, we take a general formula and adapt it to our specific situation. So I will call it, say, we're looking for the thing in glass. So let's say the angle in the glass multiplied by the index of refraction in glass multiplied by the angle in glass equals the index of refraction coming in multiplied by the sine of the angle coming in, like that. I'm going to write it this way to illustrate how that works. It doesn't matter, if you look carefully, it doesn't matter which side I put the G's and the I's on, right? It doesn't make any difference. The thing that you have to do is make sure that like goes with like. So glass and glass together here. Incoming ray here. So you have to have it set up that way. Now, we already have the ends, or the indices. We have the angle coming in, so we're solving for the angle going through the glass. So divide both sides by ng. And while I sometimes shorten this up occasionally to get to a solution, I do want to show this off very carefully here today. We end up with this. Now, to get an angle by itself, we take the inverse of the sine. So I take an inverse of the sine of the left, and I get just my angle in glass. That's fine. On the right-hand side is where it's a little tricky. You have to write it like this. Notice how it's being written. It's not that the angle theta I pops out of that. You're taking inverse sine of all of this together. Now, if it was just this, then you wouldn't have that issue. But these indices do matter. You have to keep them in there. And so this entire argument, the entire set of variables have to stay inside the brackets. So when you're doing inverse sine calculation, you need to keep those all together. All right, let's solve for angle in glass. That is inverse sine then of, what is angle that came in? 30 degrees. Excuse me, sorry, index of refraction, is 1. Make sure I say this correctly. Ng, index of refraction of glass, 1.5. And here's my angle, sine of 30 degrees. Again, notice I'm not doing an inverse on this by itself. All of this together has to stay inside the brackets. So, what do we get? Well, sine of 30 degrees is 1/2, right? And so we have a 1/2 here. We have 1 divided by 1.5 is 2/3. You end up with the inverse sine of 1/3, if you like. And the angle itself, if you end up calculating that very carefully, is 19.5 degrees. Okay, which says what? A couple things. The main thing it says is when you take a ray of light and you enter into a region of higher index of refraction, the angle shrinks. The angle gets bent inwards towards the normal, becomes smaller, okay? Now, what if we were to reverse gears, if you will, or what about talking about the angle over here once we get out of the glass and back to the air? Well, that's going to be kind of interesting because it's got the same numbers. Let me write it out for you. Ng sine theta g equals Ni sine theta I, right? That's what we just worked with. But Ni sine theta I, that's really the index in air. So Na for air, if you will. And sine theta I is sine theta A, if you will, again, angle in air. All of these numbers here, they're the same thing. So you could redo the calculation, and if you want to, I'd suggest you try it to solve for, say, theta A. But in the long run, we could just kind of look at it and see that because all the other inputs are the same, we're just reversing the calculation to solve for the other angle, we recover back the 30-degree angle. In other words, this angle here, this ray coming in like this, will be the same as this angle here coming out. These two rays will be parallel. Now, they'll be shoved over a little bit, right, because the whole ray went over a little bit. So it won't be a straight line all the way through from here to here. But this ray and this ray specifically will be parallel to each other, turns out. So the light comes in, hits the glass pane, shifts a tiny amount that depends specifically on the thickness of the pane, and then reemerges at the same angle. It keeps on going like nothing ever happened, because in angle terms, nothing did. It's in the same material, same angle. Okay. All right, last question. And it turns out that this is kind of backwards for a presentation, in the sense that this is the root cause of all of it. Index of refraction, by definition, is the change, if you will, the ratio change of the speed of light in vacuum, which we call C, we're still calling it C, divided by the speed of light in this new substance. So, say, pane of glass. Now, if we take that and turn that around, the speed of light in glass equals then the speed of light in vacuum divided by index of refraction. So if this is speed in glass, and that's index in glass like that, 3 times 10 to the 8th meters per second divided by 1.5. Notice, by the way, because index of refraction is a ratio, that there is no units on index of refraction. 3 divided by 1.5 is 2. And so the speed of light is still pretty fast by any reasonable standards, of course, but it did decrease a substantial amount. It went from 3 to 2. It's cut down by 2/3 of the original value. So that's a significant change in speed. And the reason to sort of talk about it that way is that the reason that we have this index, or this refraction formula here, this law of refraction, ultimately is coming from this statement here, that the speed of light changed. That's why the light bent. That's why the angles change in the first place, is because the index of refraction changed. If the index of refraction doesn't change, as we saw before, the angle doesn't change. The angle is the same. So that's kind of an interesting thing, and that tells you a little bit about why rays of light coming through your window work the way they work. Our technical support staff is Sidney Gautraw and Sophia Turner. Funding is from the Universities of Mississippi and Southern Mississippi. We shoot these videos in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla, thanking everybody for your attention as always, and clear skies.